Hello, everyone. Good afternoon. I want to welcome you to today's lecture. Once again, Emeku Denze is on the line, and today we're going to be talking about nomenclature of covalent compounds. Let us take it away from there. We have a few learning objectives that we want to cover in this lecture, and those include number one, we'll explain how covalent bonds are formed. So in this, we're going to take time here to talk about how covalent bonds are formed. We'll describe the characteristics of covalent or molecular compound. Those are compounds formed. Those are compounds that are formed from the formation of covalent bonds. We'll describe the types of covalent bonds. We'll briefly talk about this. We're going to come to it again. And finally, we'll focus mainly on naming correctly covalent compounds given their formula. And finally, we should also be able to write the formulas of covalent compounds given their name. So let us take it away from there. Now, let's talk about covalent bond. A covalent bond is a type of bond in which, of course, like I said before, both ionic bond and covalent bond, octet rule must be satisfied. So in this type of bond, octet rule is satisfied when two atoms share their valence electron. Remember, the valence electron is the electrons that actually go into chemical reactions. So when two atoms come together, instead of when we compare it with the ionic bonds, in ionic bonds, the metal loses the electron, whereas the non-metal accepts the electron. In this case, no one is losing, no one is gaining. Or rather, everyone is gaining. Let me put it that way. No one is losing, but everyone is gaining. So what happens is that these two atoms come together to share their valence electron. And in doing so, they actually each of them fulfills their octet rule. So the shared electrons are counted for the octet of each atom that shares them, as I'm going to show you below. Now, hydrogen, this is the Lewis structure of hydrogen, because hydrogen has only one proton and one electron, the neutral hydrogen in its outside shell, and another one here. Now, for hydrogen to satisfy the octet rule, it wants to look like helium, which is the closest noble gas that has two electrons, right? So what it does in this case is that two hydrogens will come together here to share this one electron to make it two. So that in each case, this hydrogen now has two electrons counted from this. The other hydrogen to the right also has two electrons. And the shared pair of electrons here are counted for each octet. And here, both of the hydrogens have achieved their octet rule or octet number of 2 without having to lose anything. But in this case, both of them have shared the electron. Now, the attractive force that actually forms when atoms are both attracted to this shared pair of electrons is what we call the covalent or molecular bond. This attractive force is what we call the covalent bond. And the compounds that result from the formation of this covalent bond are what we call the covalent or molecular compounds. So the covalent or molecular compounds are compounds that have covalent bonds in them. So this is what happens. So now if I redraw this again, this is what I'm going to have. I'm going to have a hydrogen that forms a bond with another hydrogen. So this bond, of course, is the covalent bond. And I'm going to show you more pictorial illustration that explains the formation of covalent bond. So what happens here now, this is, of course, you know that the electrons exist in a cloud. So this is my kind of cloud here. This is my kind of cloud. Now, each hydrogen atom has one electron in the outermost shell. Both of them are coming together like what I showed you earlier. So when they come together, look at what happens. Both of them come together within that cloud and forms this pair of electron, which counts for the octet of each. And this particular pair of electron is what represents this particular covalent bond that is from here. So I try to explain to students that think of a covalent bond as a tug of war between two people with equal strength, where they are dragging, but nobody is actually winning the race and dragging each other down. Where both of them have the strength, dragging each other, but nobody is actually winning the race, right? So the bonds are there. Now, there are situations whereby one of them might at some point begins to win the race. We're going to talk about that. That will result to what we call the polar covalent bond. So let us see this covalent bond as a tug of war, where the two people are just standing there, holding the rope individually, and they are getting a share from that rope, and no one is actually winning the race. So that is a good way I can explain the formation of covalent bond. So what are the characteristics of covalent compounds that are formed that have covalent bond in them? What are those characteristics? Now, the characteristics are opposite of the characteristics of ionic bonds. They include the following. They have low boiling and melting point. Of course, when you compare them with ionic bonds, that have the ionic compounds that have high boiling and melting point, because the covalent bond is much weaker than the ionic bond. It takes less energy to break down, and that is why they have low boiling and melting point. They are poor conductors of heat and electricity. A few of them do, but majority of them do not conduct heat and electricity. So generally, let's say they are poor conductors of heat and electricity. They are soft and flexible. Now, most of them are actually flammable. They are flammable than ionic compound. What this means, simply means, is that they can easily catch fire and begin to burn, just like your gasoline. A good example here is the gasoline is a good example. Your gasoline, kerosene, and most organic compound, the class of alkanes and alkenes, alkynes, and all the rest of them. Benzene. These are all examples of covalent compound. Because they don't have any, they are not polar. They are mainly insoluble in water and other polar solvent. However, they are polar. They are soluble in non-polar solvents like benzene and maybe carbon, other just non-polar solvent. They are generally soluble in non-polar solvent, but for polar solvents, they are not soluble in them. All right, we now move to the next slide. So what are the two? There are two types of covalent bonds that we're going to be talking about here. There are two types of these covalent bonds we're going to be talking about. Now, the first one we're going to talk about now is already the one that I've already explained. The one I've already explained is what we call the pure covalent, the non-polar ordinary covalent bond. Now, it's easy to grasp this type. In this type of covalent bond, sharing of electrons are equal between the two atoms that are involved. The two atoms that are here are sharing equal amount of electron because their strength is almost the same. They usually form from homoatomic molecules, just like examples is the hydrogen, nitrogen, oxygen. In this case, if I use the hydrogen that I used previously, remember hydrogen shares an electron with another hydrogen. What it forms is the covalent bond. The strength of these two hydrogens are the same, right? Making this a pure covalent bond, whereby no two hydrogen is gaining more electron than the other, right? So in this case, now the ability of any atom to actually attract electron to itself, a shared pair of electron to itself, is what we call electronegativity. So atoms involved in this type of covalent bond have a similar affinity for electrons. That affinity is what we call electronegativity. It's like similar power, right? When their power is the same in that tug of war, nobody's winning the race. This type of bond is what we call, this type of covalent bond is what we call pure covalent, non-polar covalent, or ordinary covalent bonding. However, in polar covalent bonding, in this case is the opposite. Now, here, the electron pairs are not shared equally between the two involving atoms. Now, one atom has higher power, that higher electronegativity, higher affinity, higher macho power to attract more electron for themselves other than the other. So in this case, because one has more power than the other, that molecule is polarized. So the molecules such as water and ammonia are polar due to unequal sharing of electrons. Now, what happens because of this unequal sharing is that it forms a polar bond, whereby one of the bonds there becomes highly polarized. And when this thing happens, it results to a polar covalent bond. And that particular molecule is called a polar molecule or a polar covalent molecule. Again, to show you a pictorial representation of this, I'm still going to use the tug of war. Look at this tug of war. Now, look at this one now. At this side, there are about 4 people. On the other side, there's only 2 people. So it makes sense that those of them at this point might be getting much more bigger share of this pool than the 2 that is what on the left side. So think of that as the type of polar covalent bond. So that is what happens. Now, I'm going to show you this picture. Look at this picture now. This is the space filling model of water molecule here. Of course, water molecule is oxygen now connected to 2 hydrogens on both sides. Now look at what happens here is that You see, hydrogen is very big here. The reason why it is very big is because the atom itself is very big, and then it has higher electronegativity, thereby getting more shared pair of electrons themselves, and hence having a bigger size. You see, it is bigger in size. It is bigger in size because it gets more electron than the small hydrogen here, not getting enough. The result of this is that if you draw a pole from this side of the positive to the negative here, you see this bond become actually polarized because of this unequal sharing of electron. And if you look at this, this is actually the 3D model. This is the 3D model, or the 3D Lewis structure of water. That's actually what happens again. So here, you know, water molecule, because this oxygen here has more power than this guy, it gets more electron than the hydrogen. So what happens here is that it has more pool of this electron in this bond, and actually gets a little bit more electron than the hydrogen because of that macho-ness. That macho-ness is what we call the electronegativity of the atom, the electronegativity. So electronegativity actually measures how much an atom can pull electron in that shared pair space of forming a covalent bond. We're going to get back into this much later in this class, but for now, with this introduction, we're going to take it to the main thing we're going to be focusing in this class, which is naming covalent compound. So there are two types of covalent compounds here. Through the naming scheme, I'll be dividing covalent compound into two broad areas. The first will be the binary covalent bond. Those are the ones that contain two elements in them. They just contain two elements. And then the other ones is the acid. The acid is any substance that will at least have a hydrogen in it. A hydrogen in its molecule, written first. The hydrogen has to be written first. Now, there are two types in this case. In naming the binary ionic compound, we just use the Greek prefixes. And then what happens is that if we use the Greek prefixes, we use it to indicate the number of atoms that are present in each element. And again, we name the first element first, followed by the second element as if it were an anion. We're going to see how this goes. On the other hand, in naming acid, there are the binary acid, which actually contains two elements, hydrogen and another element, whereas the ternary ones are those ones that contain more than two elements. And what makes them more than two, just like when we did in ternary ionic compound, is because the presence of what? The polyatomic ions. So in this case, we divide them into two and go down. I'm going to tell you what happens here. For binary ionic compound, what we simply do is to use hydro at the beginning of the name, and then add the stem name, and then put IC. So if it's chlorine, you say hydrochloric acid here, hydrochloric acid. And in this one, what we do is if the polyatomic ion ends at ATE, we said IC acid. In this case, if I have carbonate, I'll say carbonic acid. Carbonate, carbonic acid. And then if the acid ends at ITE, we now say what? We now say os acid. So if you have nitrite, it will be nitrous acid. So this is the common naming scheme that I've just presented, but I'm going to move on now with going deeper into each of these classes. So naming binary ionic compounds. So naming binary ionic compound is very simple. It's just easy to do. So what you do first is to give the name of the first element in full, then the name of the second element as though it were an anion. So in this case, remember the ions with the anions, the hydride, the fluoride, the chloride, each of them. So we still use that as we used in our ionic bond. So, but what differs now is that we have to indicate the number of each type of atom that is present in the molecule by means of Greek prefixes. These Greek prefixes, it is your responsibility to memorize them. 1 is for mono, 2 is for di, 3 is for tri, until you get 10 is for deca. So you should be able to memorize all this. So the prefix mono is not used for the first element. If the first element has only one atom, do not use prefix for them. But if it has two till 10, you have to use it. You have to use that particular, you have to use the prefix. But the second element, it doesn't matter. The second element, whether it has 1 or 2 or whatever, the prefix must be used. And it's important, like I said again, it's important to practice how to do this in your worksheet and in class, so that will be able to memorize these prefixes because these ones are not going to be provided in your test or your assessment. Okay? All right, let us now take it away from there. Now, let's take it away from there. Let's do some examples. It says, name the following binary covalent compounds. Again, just because this is the first time, I provided the list of what the polyatomic, the Greek prefixes, and then the periodic table. You always need the periodic table at any point in time. Here, let's name them. This is nitrogen, this is oxygen. Now, there are 2 nitrogens here, and there is 5 this here. So remember, 2 simply means what? Di. So this is going to be di-nitrogen. The next one is, this is 5, and is oxygen. 5 is penta. Penta oxide. That's how we just name it. It's very simple. Here I see S2 is what? This is carbon. Like I said, you don't say monocarbon. If it is the first element that has only one, do not put mono. We're just going to say carbon. Since this is 2 and it's sulfur, we're going to say what? Carbon disulfide. And the last one here on this page is silicon. Of course, you should know that it's silicon, right? If you always use your periodic table to check those out. So if you check it out there, silicon, of course, is listed there. You look at the formula, you know what it is, and then you name it. So this is going to be, since there are 3 here and there is 7, so this will be tri-silicon. Then this is 7 hydrogen. It's going to be hepta. If you look at the 7 here, hepta, then hydride. When hydrogen forms an anion, it is called hydride. Do not forget that. Then we go to the next one. Let's do an example again. It says, name the following binary covalent compound the same way. X is xenon. If you go to your periodic table, you go to xenon here. So this, and it's only one, no need to put mono. So xenon. Now this is chlorine, but it has 6. So remember, 6 is what? Hexa. So this is going to be hexachloride. The next one is nitrogen and fluorine, but this is 2, this is 1. So since this is 2 here, we have to put it. So it's going to be di-nitrogen. Then 4 is tetra. This is di, remember that? Then 4 is tetra. So it's going to be tetrafluoride. And the last here, but not the least, this is selenium. Selenium is in group C. So you can always look your periodic table off for that. So this is, no need to say monoselenium, we just say selenium. Then this bromine, this is bromine. This is bromine, of course. Bromine is in group 7, but it has 8. So this is going to be octa. You name it as an anion, bromide. Yes, that's how you name that. So now let's go from having the formula to writing, having the name to writing the formula. So let's start with this one. This one says dihydrogen monosulfide. Like I told you, the second element, you have to put the prefix no matter. Dihydrogen means di, means 2 hydrogen, H2 as a prefix, sorry, as a subscript, and the mono, only 1 sulfide. So this is dihydrogen monosulfide. The second one here says diarsenic pentaselenide. Diarsenic pentaselenide, right? So what are we going to do here? Is easy. We now say AS2 is 2 diarsenic, and then pentaselenide, 5 selenide, SE. Of course, selenide, SE5, SE5. Then the next one says silicon tetrabromide. Silicon tetrabromide. So let's do it. So here, silicon is, of course, Si. You can always look that up. Si, but it's only 1. Tetrabromide means bromine is for SBr4, SiBr4. That is how you write the formulas of those. Let's do one more of these two. Again, by this time, you should be memorizing your prefixes. And before now, also the anions too. And again, one thing interesting is that these covalent bonds are composed of what? Both non-metals. So it's composed of a non-metal and another non-metal. That's what they are. So they don't have metal in them at all. So they're composed of non-metals plus a non-metal, right? And it could be 2 at least, it could be 3, and even more. So it said write the formula of the following binary covalent compound. In this one, it says triselenium hexabromide, triselenium hexabromide. So selenium is 3, Se3, and then hexa 6. Hexa means 6. Hexabromide, not hydrogen. Hexabromide, Br6. Se3, Br6. Of course, if you look at this now, you'll be tempted to simplify. No. Do not simplify when you are working with covalent compound. In ionic compound, you can. Here, this is diboron trinhydride. Boron is B, and it's 2, diboron, and nitrogen is 3, tri here. You put it down there. And finally, this one here says phosphorus, which is P. Phosphorus is P. Pentaiodide, this is iodine, and penta means 5. You put it I subscript 5. So this is how you do these problems. Let's get to the next one. Let's now talk about nomenclature of acid. Now, what are acids? Acids are characterized by ionizable hydrogen. These are substances that have hydrogen in them, usually written first in front of their formula. This hydrogen is known by its ability to ionize, to be released when it is soluble in water. So acids are mainly aqueous solutions, right? So that is what they are. So there are 2 classes of acid we're going to be talking about here: the binary acid and the polyatomic ternary or oxyacid. The binary acid, like the name signifies, contains only 2 elements, including a hydrogen. Now they are named. How do we name them? Like I showed you earlier in the flow chart. They are named by adding the word hydro at the beginning of the anion name, and then the ending of the anion ending ic acid. The acid is their last name, has to always be there, right? See an example. There are 2 elements here, hydrogen first and chlorine. This is hydrogen and this is chlorine. But here in this case, what are we going to do? Chlorine is a chloride. We're not going to be using the word we did earlier as a chloride. Instead, we're going to remove that IDE and replace it with IC. So in naming this guy, we say hydrochloric acid. On the other hand, for polyatomic ternary or oxyacid, what we do? These ones contain a hydrogen, oxygen. That's what we say oxy. They have hydrogen, oxygen, and another element. So that's what we call them ternary or polyatomic acid. They contain more than 2. Now, they are named by changing. They are much simpler. What you need to do is change the name of the polyatomic ion by dropping the end in AT and putting ICE. Now, there's another group where you can drop the ID, but we're not going to talk about that. But we're going to try to make this simple. So if you drop the end AT, you just put IC and then acid. So this is, if you have your nitrate here, you have a nitrate, which is NO3. Well, let me write that well. It's NO3 minus, right? If you use it to form the acid becomes this. How do you name this? You're not going to say hydro anymore. You just say nitric acid. So they are much more easier to name because you're not putting the word hydro in front of them, right? Because this acid is derived from nitrate. Okay, I need to put minus here. Nitrate. Okay, let's practice some of those nomenclature now. It says, name the following binary acid as aqueous solutions because they are usually aqueous solutions. HI, of course, because they contain only 2, their binary, you're going to name them as what? As ic acid, right? Hydro, you start from hydro, this will be hydro. Hydro, you put iodine, but this time you say iodic. Hydroiodic acid. So what you're changing is the IC here and the acid you're adding. Hydroiodic acid. This one becomes hydro sulfuric, sulfur. This is sulfur, so you say sulfuric acid. Hydrosulfuric acid. HF, this one becomes hydro, of course, let me write the hydrofluoric acid. That's how you name the binary acid, hydrofluoric acid. Then, now we have the the names of the acid, right? Let us now write their formula, just like we've always done. You can use your crisscross method or your balancing of equation. So you say write the formulas of the following acid already named. Hydrochloric acid, what are you going to do? Hydrogen is always, as an acid, will be 1+, of course. When it ionizes, it's just 1+, right? When it loses an electron. Here, and chlorine is always 1-. So what you simply need to do is to change, since they're equal, 1, 1, what you need to do is just to bring down the name of the acid. That's it. Hydrobromic acid, of course, hydrogen is 1+, bromine is in group 7 is 1-. Again, remember that. Look at the periodic table. And most of these guys are formed from the ones from group 7, which all have a charge of -1. So this and this is going to be HBr. And the last one here, the same thing. This hydrogen is 1+ plus iodine is 1-. If they exchange their magnitude of the charge, which is 1, 1, you're going to have Hi, this hydroiodic acid. So if you're watching this video, you can always pause them, practice this yourself, then turn on the video again, look at how far or progress you made in getting the answer yourself as you watch. And you're always free to adjust the speed as you watch them on YouTube. Let's go to the next problem. In problem 7 here, it says, name the following ternary acid. Now we're going to ternary acid, the acid that have more than 2 elements. Here you have hydrogen, sulfur, and oxygen. Remember the rule. Now this is sulfate. This is derived from sulfate, right? This is from sulfate. Sulfate. And sulfate is SO4, 2-. So what do you simply need to do? We're going to drop we're going to drop AT and put ICE. And there's no hydro. So what we're going to say, we're just going to say, in this case, we're going to say sulfate. We say sulfuric acid. That's what we did. Just drop this and then use the stem name sulfuric acid. What about this one? This is from phosphate, PO3, 2-, which is phosphate. This is phosphate. So what we're going to do, we're going to drop this and we're just going to say phosphoric. We put ICE here, IC here, and then say acid. You have to always say the word acid at the end of them. This one again, okay, here, this is some carbonate. This is from CO3. From CO3, 2-, which is carbonate. This is carbonate. So how do we name it? To name this one, we're going to say carbonate. We drop this and put ICE, carbonic, and then we put acid, carbonic acid. That is how we name it. So these are the names of these ternary or polyatomic acids. Let's now go to the last problem, the last but not the least, where I did the mixture of all the acids. So write the formulas for the following acid. Start by nitric acid again. I'm just going to say nitric. This is, I'm going to change the color of that. I like using my green. So this is H+. Nitrate is 1-. Remember that? So if you exchange their charges since they're equal, what they're just going to do is just say HNO3. That is nitric acid. On this next one, hydrosulfuric acid is hydrogen and sulfur. Sulfur is 2-. You exchange your radical or exchange the charges. So this will give you H. Hydrogen will not take the 2, sulfur will not take the 1. And then sulfuric acid here. Remember, sulfuric acid is a polyatomic acid. It's a ternary acid. So it came from sulfate, right? It came from. So you put your hydrogen, and then it came. Remember your sulfate. So sulfate is 2. These 2 will go to this guy. 1 will go to sulfate. So it's be H2SO41. But you don't need to show the 1. That is sulfuric acid. And the last here, but not the least, is hydrobromic acid. Again, I talked about this one earlier. Hydrogen is 1+, bromine is 1-. The charges are equal. They are balanced. Just say HBr. All right. So that is how you write the formulas of this acid from their names. And having said that, we have actually come to the end of this lecture. Thank you for following up and listening. Bye.